An example of ideal non-inverting amplifier or op-amp shown here. First question, for what range of Rx does the op-amp stay linear? And second question, find the values of VO, VN, and VP for Rx values of 60 kilo ohm and also Rx case of 90 kilo ohm. Okay, for the first case, in order for op-amp to remain in a linear region, the value of Vout needs to be between plus 5 volt and minus 5 volt. So we can say op-amp linear requires Vout less than or equal to plus 5, more than minus 5 or equal to minus 5. And from here we can say, let's find out Vn. From KCL we can say Vout minus Vn divided by Rf is equal to, that's the current flowing this way, given that op-amp is in linear region and it's ideal op-amp, so no current flowing or no current coming out of the negative terminal, so the current that going this way should continue going through Rs. So we have Vn minus 0 divided by Rs, and as I expected, we can say Vout is equal to Rf plus Rs over Rs times Vn. And this is, as expected, the gain from negative port to output port for ideal non-inverting amplifier. Now our next move is, given that op-amp is linear, we know, and of course ideal, we know that Vn should be equal to Vp, a virtual short between the two input ports of op-amp, and we know the relationship between Vp and Vs also is Vp is equal to Vs, that's a voltage divider, so it should be Rs divided by, Rx divided by Rx plus 15k. So combining A and B, we get Vout is Rf plus Rs over Rs times, replacing Vn and Vp with this equation, so times Rx divided by Rx plus 15k times Vs. For this one, we know Rf is 63 and Rs is 4.5 divided by Rs, this is 15. So that's this gain. So we can say Vout is 15 times Rx, which is unknown, divided by Rx plus 15k times Vs. Now we know we want VO to be in this range, so let's say, sticking with plus 5 volt, if Vout is plus 5 volt, we understand that from C, we understand that 5 is equal to 15 times Rx divided by Rx plus 15 kilo ohm times Vs. So we can say from this that and Vs is 0.4, by the way, so we can say 1 is equal to 3 times 0.4 times Rx plus 15, and from this we can say Rx plus 15k is equal to 1.2 Rx, which means 0.2 Rx is 15k, which means Rx is 75 kilo ohm. So Rx need to be less than or equal 75 kilo ohm in order to having VO limited to the target range of 5 volts, so that op amp stay in linear region. So we know the answer to 1. And now for 2, it's easy. If Rx is 60K, because it's less than this, we know op amp linear region, and we can easily say, going back to the same equation we found here, we can find out the value of VO. So we can say VO from C, this guy, is 15 times 60K divided by 60 plus 15K times 0.4 volt, that is the Vs, which means V out is equal to 4.8 volts. This is 1 over 5, 60K, my bad, 60K plus 15, that is 4 over 5, and 4 times 3 is going to be, yes, we get to 4.8 volt. So that is the value of V out. Now if Rx is equal to 90K, from this we know Rx is already violating the range for the op amp to stay in linear region. So we know op amp will be saturated, and from this we know V out, because of op amp saturated, will be plus 5 volt, maximum value of supply voltage. And also to compute the value of Vp and Vn for the first case, since op amp is linear region, we know Vp is equal to Vn, and it's easy to compute Vp because Vp is just the voltage divider between Rx and 15K, so it would be 60K divided by 16 plus 15, which is 4 over 5 times Vs, 0.4 volt. Here, in this case, the first part is true, so we can say Vp is, again, Rx over Rx plus 15 times Vs, which means is 90K divided by 90K plus 15K times 0.4 volt, and this is 6 over 7 times 0.4. That's the value of Vp. But for Vn, now op amp is saturated. Because of saturation, we know Vp is not anymore equal to Vn. Vn needs to be found through the KCL, as we discussed before. So we know V out is Rf plus Rs over Rs times Vn, which means, as we computed before, it's 15 times Vn, but V out, because op amp is saturated, in this case is 5 volt, so we know Vn is 5 divided by 15 is 1 over 3 volts. So now you can see the difference between these two scenarios.